Hi everyone, and welcome to the video on sections 2.1 and 2.6. So in this video we're going to be talking about both sections because the ideas are related. Now in 2.1 you're going to deal with the tangent line, and in 2.6 we're going to introduce something called the derivative. Okay, so both of these things are all about the idea of change. And really, calculus as a whole is all about this idea of change. And so we're going to see lots of examples, some of them real-world examples, where we are interested in how something's changing and how that change, especially over time, how that accumulates. So if we understand how something's changing over some time period, what does that tell us about the thing itself? And so to kind of ground this in a few examples, we could think about something like bacteria in a petri dish growing, right? So if we understand how that changes, how the bacteria is multiplying, we could take that knowledge and apply it directly back to the bacteria itself. Okay, so knowledge of the change in the bacteria population gives us a bunch of good information. So you'll see a bunch of other physics-y type problems like throwing balls, random stuff like that, rocket ships, all that kind of stuff. So physics, if you go take an intro physics class, when you go do that, or if you have already, I want you to think back. A bunch of the stuff you learned is centered around thinking about change. Now, go back to your physics equations, and I am sure that either in the equation itself or if you look in your book how the equation comes up, how it's derived, they probably started with thinking about something changing. So like speed or velocity if you have direction. Acceleration, right? Acceleration being connected to forces. F equals ma is the one you use all the time. Well, what it's talking about here is trying to relate forces, like on an object, to change. Acceleration is change. So it's all about change. This also shows itself, of course, in so many ways more than I'm going to mention here, but in economics and finance. So in a simple version of this, things like loans and savings accounts, right? How do those things work? There's constant change there, right? Your savings account will grow. Money will be put in. How does that work? How does that change work? How do you use that idea of change to figure out how much money you'll have for retirement? You get a loan for school, a car, whatever. You have to understand how that change is going to work so that you can plan financially to pay it off, to know how long it's going to be, how much it's going to cost you, all of these things. So it's all about change in all of these different ways. Okay, so that's one of the goals of calculus is understanding change. So okay, where do we start here? Well, we start with this idea of the tangent line. So this definition says the tangent line, so just right away, it is a line. So everything you remember about lines, right away. Y equals mx plus b, and then your other form, y minus y1 equals mx minus x1. Right? So a line, I think of these two things, slope and a point. Okay. The tangent line to some curve. So I've got some function, and now there's the special line that I can draw at the point. Okay, so if I'm doing tangent lines, what do I need, right? So I'm given these two pieces. All right, if I'm going to make you a tangent line, I need you to give me a curve and some point, specific x value, which in this case they're calling a, that you're going to plug in. So this would be the line through that point with the slope, m, remember slope, we just wrote it right here, given by this limit. So look at that, limits are back again. They're going to be everywhere, provided that it exists. You don't always have a tangent line, right? Limits don't always exist. We saw that. You can have limits that go to infinity. You can have limits where the left and the right sides don't equal. All those different scenarios. You can have different just discontinuities, lots of different stuff. So tangent line, it's a line right up against a curve, just touches the curve at a specific point. And we can calculate the slope with this. So, okay, we're just going to jump right into an example so you can kind of see how this works. So down here, and we'll talk about this in a second. So down here, I have an example. So it says, if a rock is thrown upward on the planet Mars, so I'm just sitting on Mars and I throw a rock up in the air, with velocity 10 meters per second. So here we go, we're talking about change. And again, velocity, magnitude, and direction. So I threw it up in the air, okay? Something to think about that can pop up sometimes. Its height in meters, t seconds later, is given by this function. So this here is height. You give me a time, I'll tell you how high off the ground, the Martian ground this is. So, okay, find the average velocity over these given time intervals. So average velocity, averaging, right? This should hopefully make us think of like, okay, I have a fraction, top and a bottom. Well, average velocity is just change. So change in height, okay, over change in time. All right, so average velocity, change in height over change in time. Should kind of sound a lot like the idea of slope to you, right? Change it, rise over run. Same idea. All right, so how we can do this? Well, we have height here, right? And we have time given here. These are all t's. So we just plug in. These problems right here, you just literally plug in. So for I, so change in height, well, it's going to be my height at 2 compared to my height at 1. So the height at 2 would be 10 times 2 minus 1.862 squared. I'm plugging the time 2 into this height function, minus, well, 10 times 1, because I want to know, well, how high was I at 1 second? Minus 1.86 times 1 squared. So that's the change in the height divided by 2 minus 1, because that's the change in time. So altogether, you are going to end up with 4.42 meters per second. So what's that telling us? Over the time period from 1 second to 2 seconds, you moved on average 4.42 meters per second. Right? That was your average velocity over that time period. All right, what could that mean? It could mean a lot of things. Maybe from 1 to 1.5 you went really fast and then you slowed down from 1.5 to 2, or vice versa. We don't really know. Just on average, this is how fast you were going. All right, so okay, that's nice. Now, we are usually not as interested in average velocity. Average velocity is great, don't get me wrong, right? But we're usually interested in this idea of the instantaneous velocity. At a specific time period, how fast were you going? So we're often interested in this idea of instantaneous velocity. All right, average velocity is still great, but instantaneous velocity is also very important for us to find. So we want to know at the instant t equals 1, how fast were you going, right? So you're driving in a car, you could do average velocities, but if I just kind of halted time, you are moving at that time. So how fast are you going at that moment? That's what we're trying to get at. Not, oh, how fast are you going over the next 2 seconds? No, at that moment, how fast are you going? Instantaneous velocity. So how do we do this? Well, the easiest way to do this is to actually do this first. So average velocity is pretty easy to do. You plug into the function, you see the difference in your heights or in your speeds or whatever you're doing in that case. So you look at that change divided by the change in time. And so what ends up happening, this is pretty amazing that this works so nicely, is if you keep taking the average velocity, but what you do is you don't go all the way out to 2, right? That's so far. You go closer to the point that you care about, t equals 1, right? We care about t equals 1. So we keep doing the average velocity, but closer and closer and closer to 1. Because I'm interested in what's your speed at the exact moment t equals 1. We can't necessarily figure that out just by trying to measure different heights and comparing, but what we can do is we can take all of these different average velocities and then just try to get the idea what's happening to this. Is this approaching something? Because if it is, that's going to be your instantaneous velocity. So it's all about this idea of we can approximate with the average velocity, and we can make that better by getting closer and closer and closer to the value we actually care about. We actually care about t equals 1. So you see this graph here. This is our function, y, right here. So this is y. Now, what I wanted to show you from this, and then I'll fill in the rest of these numbers so you can have them. What I wanted to show you from this was just kind of like how our approximations work compared to the tangent line. So in green here is the tangent line. This was the point that we care about. And the definition, P, was that point. So that's the point we care about, right, at 1, at t equals 1. So we want to try to get the slope of this tangent line because the slope of this tangent line is our instantaneous velocity. So let me say that again. The slope of the tangent line is going to be the instantaneous velocity. Okay. Let me fill this in. So that's it. The slope of that line is the instantaneous velocity. And so what, I don't know how to do this. I didn't read what we wrote above. Okay, that's fine. How could we do this? Well, we could take 1.5, that's this dot, and we could say, you know what? That's only half a second. Why don't I just find the slope of this line and say that's pretty good? And you could look at this and you might be like, yeah, that's pretty good, but the slope is not exactly that. It might be pretty close, right? We're not too far here in terms of slopes. Like, it's okay, but it's not quite right. So you'd get that number, which is what we have over here. That's this calculation, the average velocity. But, maybe we want to do better than that. So how do we do better than that? Well, if we instead take a point a lot closer, like 1.1, that's this dot here, and we draw this line, well, ooh, look at this. Look at the pink and the green. They actually seem to have a pretty close slope, right? This pink slope, this pink line has a slope that's much closer to the slope here. And so that's this calculation right here. This does a much better job approximating the true instantaneous velocity than this one does. And if I keep getting closer and closer and I keep bringing this dot in, I'm going to get a better and better and better approximation to this instantaneous velocity. And, how do we think about keep doing it, keep getting closer, closer, closer? That's a limit. That's the way we're thinking about limits. This idea of, oh, I found this process that's helping me, it's doing something. Oh, I just want to keep doing it, but I can't keep doing it, but it would be nice if I could just keep going. That's what a limit does, is it lets us go forever, even though we can't, right? We can't sit here and now try 1.0001 and 1.00001. We can't do that, but the limit can help us figure out what would happen if we did do that. All right, so that's what's happening here. So the rest of these, and I just did this in Mathematica, and I'll put the Mathematica sheet in if you're interested to see how I defined the function to do this and just kind of what I did. So if you're interested. But what ends up happening here for these, so we did the first one. The second one, I'm going to do these in the right colors, ends up being 5.35 meters per second. This one, which I think I picked pink or red for, ended up being 6.094 meters per second. And then the next one ended up being, again, you're just using change in height over change in time for these. The next one here ended up being 6.2614 meters per second. And finally, this last one ended up being 6.278 meters per second. Okay, so again, all these just came from Mathematica. I'll post the document if you want. All I did in Mathematica was I defined the function we were using. I defined this formula that we were using, the function at this second number minus the function of the first divided by this minus this. It's the same thing every time, right? So I can make a function that does that. It takes two variables, but you'll see how I did that in the notebook. And then I just had this calculate, and I just plugged these numbers in. So pretty quick. So there you go. So we see that, okay, we're increasing, but it's slowing down, right? So that's making me think that as I get closer and closer to 1, I'm getting pretty close to the right answer here. And the actual instantaneous velocity, I'm just going to take a guess. Let's guess 6.28 meters per second. Oh, I'm right. Excellent. Great guess by me. Of course, just looking at this without actually knowing the end answer, you could have guessed something different, 2.79, I don't know, it's fine. Just as long as your guess fits this pattern. It's going up still, right? Look, I'm going up, 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 but that's slowing down quite a bit, right? It jumped, what here? It jumped quite a bit here, almost 0.7 meters per second. Then here it jumped much slower, only 0.17. Here it jumped even less than that, just under 0.02 meters per second was the jump here. So that's a very small. So you would expect then, if you kept going, it would go up even less and less each time. So, like 6.3, that would be too big because we already see that we're not jumping up by that much anymore. So 0.28 is reasonable. But, that's okay. If you guess 6.3, that's not bad. So there you go. Instantaneous velocity, instantaneous change. How do we get this? Well, we know how to do average change, not too bad. So do that, but then keep getting closer and closer and closer to the point you want, and you'll get a better and better and better idea of what's going on here. Okay, so this idea of the tangent line gives us our first taste of the next big idea, the derivative. So tangent line, just to review, it's the line at a specific point of some curve such that it goes through that point, that's also on the curve, just touches it, and the slope of that line is given by this limit. All right, so the second box here is a different way of thinking of this formula. They're both useful. Sometimes one is easier to use than the other. All right, but they say the same thing, and you should think about that. I could think of this as like, okay, I'm going to be plugging numbers in that are closer to A, or sorry, closer to A. So like in this case it was f of 2 and then A was 1. So like, okay, 2 minus 1. And then it was 1.5 and 1, and then 1.1 and 1. Or I could think of this a little differently and instead be like, well, really what I'm doing is this is just always 1 plus a little bit more, right? So f of 2 is just f of 1 plus 1. So this h here tells us, this distance here that we're actually going out. So here, the distance is h is 0.5 to get to this dot. And then h here is 0.1. So then hopefully it's not too bad to look at this and say, okay, yeah. What I'm doing here is I'm just letting h, the distance between the point I care about and the test point I'm using, I'm going to let that get smaller. That's just what this says. It's not viewing it as two distinct points anymore, really, like a and x. It's viewing it as just all in reference to a, the one I care about. And I'm just letting the distance between a and my new number get smaller, all the way to 0. So let's now talk about the derivative. So we have a new definition. This is called the derivative. So this is now getting into 2.6. The derivative of a function f at a number a, and this is the notation we will very frequently use, f prime of a. So this would be just if we're talking f prime. Okay, so f with the little prime. And that's given by this. F prime of a equals, and then, oh, this limit looks really familiar, right? Hopefully that's not too bad. This is the limit we literally just saw up here, right at the top. So you might be looking at this being like, wait, what's the difference? There really isn't one. This is m, the slope of the tangent line. So the derivative is a name we put on this slope because it is such an important idea. And it actually ends up being more than this too. But just for a specific number that we want to plug in, it just looks like the slope of the tangent line. So this idea we cooked up for instantaneous velocity, right here, this idea we cooked up for the slope was so good that we gave it its own name called the derivative. All right? And what's really neat about this idea of a derivative is it's something that we define to start at a specific point. Like, oh, you got to give me a point to do this idea of a derivative. But it just so happens that we can extend this idea to a whole big range of x values. So instead of taking a function specifically at this value a, we can define the derivative over a ton of points. So you might be like, well, what do you mean by that? Well, think about this picture again. This specific point P, was there anything special about this point? No, not really. So could I have found the tangent line at, a point over here, or over here, or over here, or here, or here, or here, or here? Yeah, I could find a tangent line to any of these points. So that tells me that for any of these x values, I can find this thing we just talked about called the derivative. So let's stop for a second. You're telling me I can plug in a bunch of these different x values and get out a number, right? Because this slope is a number, right? So I plug in a value, I get out a number. I plug in a value, I get out of a number. Oh, so this is just a function too, right? The derivative is a function because I can plug in a value a. Okay, you give me that number, I draw you the tangent line, I get its slope, and that's the number I give you back. That's a function, right? So, okay, I can define this derivative, and it is actually a new function. All right, very, very important idea. All right, so let's try an example with this limit and see what happens. We've got this idea here. So we're going to start this off by picking an a just so that we can use this definition to start. So let's try a is 3/8. Okay, so we've got this function, we've got this a value. Now, we've got these two formulas up here, this one and this one. So we'll try them both and see what happens. We'll just set them both up. So, okay, the derivative of this function at 3/8 is equal to, we'll start with this one because we can see it, the limit as x approaches 3 over 8 of f of x minus f of 3 over 8 x minus 3 over 8. Okay. So we can also set this up separately as f prime of 3 over 8 equals the limit as h approaches 0 of f of a plus h minus f of 3 over 8 over h. Okay, so it's up to us kind of how we want to do this. Let's simplify these maybe a little bit so we can get an idea if one's better than the other. Limit as x approaches 3 over 8. F of x is 1 minus 2x under the root. If I plug 3/8 into here, I'm going to get 1 minus 6 over 8. Okay, so that's 2/8, which is 1/4, and so the square root of 1/4 is 1/2 over x minus 3/8. And then this one then would be limit as x goes to 3/8 of 1 minus 2 times 3 over 8 plus h minus 1/2 over h. So at this point, it's up to us which one we want to try to do. They look very similar to me. I guess maybe we could think, oh, there's some extra stuff in this radical maybe we don't want to deal with, so let's stick with this one. All right, so if we remember back to earlier in chapter 2, we knew how to deal with these limits by trying to get rid of the square root on top here. Now again, you should always check by plugging in, but if we plug this in, we're going to get 0 here and 0 here. So good algebra practice to check that, but that's what's going to happen. So then remember how we did this. You multiply by the same thing up here, except you put a plus sign, right? That was the trick we've used before. So then let's see if it works this time. Okay, so up top first, this one is going to hit this one. Same thing multiplied by itself. So let's write the limit again and see what happens. We're just going to focus on the top again for a moment. Those are going to hit. The square roots will go away. That becomes this. Boom, boom. Okay, then you get this one times the plus half, this times the minus half. Those will add and cancel, and you'll end up with this. Okay. Now down here, you end up with that factor times all this thing. Okay, so we got rid of the square root on top. That's pretty nice, right? So let's simplify here and see what happens. We got the limit as x goes to 3/8. Okay, so then this was going to be 3/4 minus 2x, just comboing these constants. All right, so we're looking at this kind of like, I don't see what's happening maybe, but we can do this real tricky thing, because what has happened in the past was we were able to do something up here so that we could cancel. And I know it's tricky, but we can actually cancel. Watch what happens. I am going to factor a 2 out of this. So I'm going to show you that over here. 3/4 minus 2x. Factor a 2 out. Take a 2 out of that. Left with an x. Okay. Now, take a 2. There's no 2, right? Well, just take it out anyway, right? How do you mean take a 2? Well, let's do this. 2 up here, 2 down here. Did I change this? No. I multiplied by 1, 2 over 2. But if I take the 2 out here, I still have it left here. So, haha. Oh, look at that. That looks a lot like this one. Oh, but I'm not quite, right? This is positive, this is negative, and it's flipped here. Well, how do I deal with that? Take a minus out. That puts a minus in here and a plus, and boom, look at that. So we actually end up with, get down there, we actually end up with the limit as x approaches 3/8, okay, and then what was on top? Negative 2 x minus 3/8, x minus 3/8 times all this stuff, and we're looking good because cancel, cancel, and then now after those have canceled, we can just plug in, and so we can then plug this in, and this is going to end up giving us negative 2 over square root 1 minus 2 times 3/8 plus 1/2. Okay, and then we actually did this calculation earlier. This is going to end up giving me 1/2, which means negative 2 over 1/2 plus 1/2, which is negative 2. This is the derivative of this function at the point 3/8. So for some reason, if this was your height or distance or something like that, and x was time, just as an example, then we'd be saying at time 3/8, whatever the units are, you would have a instantaneous velocity of negative 2 and then units. So there you go. That's the derivative. Now, the way that you need to think about this in terms of the derivative being a function is, what was special about 3/8? Was there anything special about 3/8 here? And you might say, well, yeah, it's nice when you plug it in. True. But does it really matter if I plugged in, instead of 3/8, 2/8? This wouldn't be as nice, but that shouldn't change anything I do here. I'd still do the same process, multiplying by the plus 1/2 instead. None of that would change at all. I mean, this number would change, and the 1/2 would change to a not nice number, but that doesn't change this process. I'd still be able to do this, cancel, plug in, get a number. So what just happened here was I said, okay, take 3/8, plug it in to this derivative, and I spit out negative 2. That tells me this idea, that's this derivative, is actually a function because it's taking inputs and spitting out an output, right? And so what's the notation for that? Well, the notation for that as a function is f prime of x. And all this is doing, you can think to start, is, well, it's just saying, okay, if you give me a number in the domain of f and I try to plug it in, I'm going to take that limit that I defined above, I'm going to try to find the slope of the tangent line at the number you give me. That's it. That's what this derivative is saying. Give me a number, I'm going to go up and look at my function and try to find the slope of the tangent line. That's it. So that's the derivative. Geometrically speaking, that's what the derivative is trying to do. All right, so it's a function. We can evaluate it at a specific point, but one thing we're going to be able to do also is, instead of evaluating it at a specific point, we can also in the future evaluate it and have a variable still hanging out there. And one way you could try doing that is, instead of giving a specific number here, just make it a general A. Plug it in, you'll spit out a number. So we can totally do that. That's going to be something we want to play around with, is having this limit, but we're going to have this parameter A that's just acting like a variable. But also remember, you treat it algebraically like it's a number, and we're going to run it through this limit process, and we'll get a formula for f prime. All right. So let's try another example. In this example, we're kind of taking things a little bit differently. They're giving us a limit set up. And so what the problem asks us to do is to identify what function and what point are we trying to do the derivative of. So, okay, this is the limit that was set up from a derivative. So this is f prime of a, and the question is, what's a and what's f? Right? There's a function, there's a point. So what is it? So okay, we got to go back and think. The limit as x approaches a of f of x minus f of a over x minus a. That was our definition that we had set up, one of the two formulas. So if we just do a little mix and matching, it's actually not too bad to figure this out. Here's f of x. That's supposed to match here. Okay. Here is f of a. That's right here. Okay. And then we've got this is supposed to be a. All right. So, oh, cool. That's not too bad. So then f of x is 2x. Neat. All right. What else? Well, a is going to be 5. And then as a double check, right, f of 5 is 2 to the 5th, which is 32. So awesome. That's exactly what we were hoping it to be. So there you go. So that's an interesting, pretty neat example of trying to kind of work this definition backwards, which is, always a really important idea. All right? So hopefully that's not too bad. Let's try one more example to try to get you a little more comfortable with the idea of the derivative as a function. So we're going to throw in another example here. We're not going to make it a crazy one. I just want to show you what this looks like. So let's let f of x equal x squared. Now, I want to find the formula for this function. Because like I said, the derivative is a function. You give me a value, any number you want to give me. In this case, sometimes the domain is not anything, but in this case, it's all reals. So in this specific case, I'm saying you give me any number you want. What can I do? I can take this function, take that number, find the slope of the tangent line, and that will be what f prime is for that specific number. Okay, how do I do that? I want a formula. I don't want to do a limit every single new number you give me. I don't want to do another limit. Stop that. So here's what we're going to do. We're going to do this f prime of a, but we're going to just keep this as a. Just let it stay a so that I can pick a later. Watch what's going to happen. So remember, this is the limit as, and then we've got a couple different ways to do this. Again, you can do x approaches a, or you can do h approaches 0, whichever one you want. F of x minus f of a over x minus a. Okay, so let's plug in here. So then f prime of a is equal to the limit as x approaches a of x squared minus a squared over x minus a. So I just plugged the function in. Okay. Well, here we got to do a little work. So let's bring it over here. The limit as x approaches a. Now x squared minus a. This is a very special type of quadratic where it factors really nicely for us. And so you could check this. X plus a, x minus a over x minus a. Okay. So then what happens? Well, oh, look at that. Cancel. Limit as x approaches a of x plus a. Once we've done that algebraic step, what do we always do? We try plugging in, and we get what? We get, plug a in, a plus a is 2a. So, what is my claim? My claim is, if you give this function, and you give me any point, right? Any point you want, any x value you want, I'm going to take that x value, find the slope of the tangent line, and it's this. So what do I mean by that? All right, let's recap. What the heck do I mean by that? This is the formula. Take this function, okay, give me any x value I want. So like, let's let x equal 4. Well, f prime of 4 is going to be 2 times 4, which is 8. That's the slope of the tangent line. All right, well, come on, that's ridiculous. You can't have done that so fast. Yep, I did. Done. Boom, 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 boom. We just found a formula for it. So the formula is right here, and I know I'm using a here. It's a little tough. We gotta do this abstraction in our head. A was a dummy variable. The real variable we want to use is x. And so we do that up here. We couldn't use x in this because then it would be x minus x, and this wouldn't make any sense. A is just this dummy variable we use until we get the formula at the end, and we want to convert back to x's. So there you go. Look, I have a formula for the derivative. Give me any x, any one at all. I can tell you what the slope of the tangent line is immediately. Now, what we'll do in later sections is find tricks, not necessarily tricks, but shortcuts to find these formulas without doing limits. Because I picked an easy limit here, right? But limits can get very, very difficult to do, right? We might even have to only just rely on numerical methods. We don't want that. We want a way to do this calculation, get this function just quick, quick, quick. So that's what a bunch of the next chapter is for. And then after that, we'll start talking about this thing called the antiderivative. And all that is, well, we don't really have too many other things in math called the anti-this, which is unfortunate. But you should think of it as the inverse. So in chapter 4, at the end of chapter 4, we'll talk about the idea of like, okay, well, we went this way and took f and made this new function. Can we go this way? Can we start here and recreate this function? And the answer is yes. And those 2 steps are the whole of Calc 1. I mean, there's more to it, but that's really it. Those are the 2 main ideas. Can you go this way? Can you go that way? We've done Calc 1. So just so you can have something to look forward to. But that was it. Tangent lines, derivatives, big, big, big idea. Lots to think about. Any questions, let me know, and I'll see you in the next video.